Imagine this. You want to send a message to a large language model. You send it to a server. It sends it to the large language model. Then it gets a response and sends it back to you. Now imagine that you don't trust the server. You really don't want its owners to be able to tell that you said hello. Well, you could try to encrypt your message, but obviously that would confuse the LLM. So it's impossible to privately query the large language model. Or is it? No, but seriously, what if I told you this was actually possible? Today, we're taking a look at the final boss of encryption. Today, we're taking a look at a revolutionary technology that is going to change the way we view privacy. Today, we're taking a look at an encryption scheme that is so powerful, and yet I guarantee you've never heard of it. Most likely. Today, we're taking a look at fully homomorphic encryption.
Fully homomorphic allows you to do encrypted computation. So there are a lot of times you want to compute something. So for example, if you're doing, asking OpenAI or GPT a question, it's doing a lot of computation in the background. But it would be cool if you could encrypt your question so that, even OpenAI doesn't know what you're asking.
Yeah.
And there's some way for OpenAI to nonetheless answer your question even though it doesn't see it. You just apply your thinking, your thinking algorithm to the encryption, and it magically turns into an encryption of your response, which the other person can decrypt.
And today, I'm meeting with Dr. Craig Gentry, the mathematician who discovered the first fully homomorphic encryption scheme back in 2009. I'm interviewing him to find out more about the history and future of the holy grail of cryptography. Before diving into the theory of FHC, let me show you an actual example. Here, we are in a Hugging Face space which can homomorphically apply image filters to pictures without ever actually seeing them. In this example, I picked a picture of Euclid, the inventor of calculus. We will apply a black and white filter to the picture. Now, we first need to generate a private key. This secret piece of data is our way of scrambling and recovering the image. Next, we encrypt the image, which turns it into an illegible representation which only our secret key can convert back to normal. We now send the encrypted image to the server. Next, the server applies the black and white filter without being able to view it. We get the image back. This bunch of random pixels is the encrypted image with the black and white filter applied. Using our secret key, we can decrypt it. We have effectively performed arbitrary computation on the picture of Euclid without having ever shared it with anyone. Pretty cool, right? Now, I've been talking a lot about fully homomorphic encryption, or FHE for short. And as you astute listeners may have guessed, there are three parts to this definition: fully, homomorphic, and encryption. Let's go in reverse order, shall we? First off, encryption has been around for thousands of years. Shout out to my boy Gaius Julius. It's a way to store data while only allowing the owner of the secret key to read it. A homomorphism, however, is a tougher nut to crack. Take a look at this commutative diagram. In the top left corner, we have two variables, x and y. If I multiply them, we get xy. Now, if we take the natural log of xy, we get the natural log of xy. Simple stuff. However, the interesting thing is that we can first apply the natural log to x and y. That gives us ln x and ln y. And then we can add these two together to get the same result. In this diagram, the natural log is the homomorphism because it preserves the structure of the data across the addition and multiplication operations. Interestingly, we can create a very similar commutative diagram by changing the natural log function to the exponential function and interchanging the addition and multiplication operations. Now, take a look at this example. Here, we start with three variables, x, y, and z. First, we'll apply an exponential function to each. Next, we'll multiply the first and second elements of this tuple together. Now, we divide the first element by the second to get a monomial. Finally, we can take the natural log of this monomial. If this all seems very arbitrary, that's because it is. Like in the previous diagrams, it's possible to end up with the same result by taking the bottom path. In fact, it's possible to swap between the top and bottom row at any time. This is essentially what homomorphic encryption is. The user finds that addition and subtraction is too computationally expensive on their machine, so they delegate it to a server, which instead computes multiplication and division to get the same result. Here, the exponential function is akin to the encryption function, while the natural log represents decryption. A well-known example of a homomorphic encryption scheme is the Caesar cipher. Shout out to my boy Gaius Julius. We can show this easily using this example. Take the word hello. To encrypt it, we'll shift each letter by 3, just like in the original scheme. So hello becomes cour. Now, this scheme actually allows us to homomorphically shift. Say we shift by 5. Now we get pumtu. To decrypt the result, we just shift the letters of pumtu by -3. We end up with mjtu, which, as expected, is our original word hello, just shifted by 5. Now obviously, this example is pretty stupid. For one, there isn't much use in shifting letters in words, because you usually end up with some nonsense, like mjtu. Also, the homomorphic operation, shifting in this case, is the same as the encryption operation, also shifting. So it's pretty obvious that it works. Still, I hope this gives you some intuition about how fully homomorphic encryption is actually possible. Also, this example helps me define the fully part of fully homomorphic encryption. You see, the Caesar cipher in this case is what we would call a somewhat homomorphic encryption scheme because it allows at least one homomorphic operation. However, to be considered a fully homomorphic encryption scheme, a scheme would need to allow any operations to be performed on the ciphertext. Fortunately, this isn't as hard to prove as you might think. Computers use bits, just ones and zeros. For more than a century, mathematicians have been studying the operations on these bits in a system called Boolean algebra. It was created by this handsome man named George Boole. Now, an important result in Boolean algebra is that you only need the addition, the XOR gate, and multiplication, the AND gate, to be able to construct any arbitrary circuit. For fully homomorphic encryption, this means that you only need to prove that you can perform any amount of additions and multiplications on the ciphertext, and then you'll be able to construct any arbitrary circuit. Moving on, now that we've defined fully homomorphic encryption, let's look at its history. In 1979, a paper posed an open problem that would lay the groundwork for what is now FHE. The paper, by Rivest, Adelman, and Dertouzos, is called On Databanks and Privacy Homomorphisms. If the names Rivest and Adelman sound familiar, that's because they are the R and A in RSA, a crypto system that still secures much of the internet today.
A brief history of cryptography from the perspective of FHE is that, first came Diffie-Hellman and RSA. And then the Rivest, Adelman, Dertouzos paper, which, basically their thought was, well, RSA is already kind of homomorphic in the sense that you kind of can just multiply the ciphertext, and that kind of induces a multiplication on what's encrypted. And then, very, very early on, actually, there were some kind of, I guess you would say, lattice-based or knapsack-based crypto systems, like in the early 80s, which were cool, but they were all broken. And so the view about lattice-based cryptography until comparatively recently, until Gentry, basically, and concurrently with Gentry, there was a crypto system called ATTRIBUTION that had a kind of a more theoretical flavor, a more solid theoretical foundation, but was also much less practical than Gentry. So basically around the same time, 97 or 98, you had these two lattice-based crypto systems which held up pretty well. So that was kind of the beginning of modern lattice-based cryptography, where people actually started to believe that you could construct something that's secure. And in Gentry's case, although I beat up on their signature scheme quite a bit, their encryption scheme held up pretty well and was quite practical. In the 90s, there was a lot of work on, as you said, somewhat homomorphic encryption. So there were schemes like El Gamal and Paye that were homomorphic for one operation. So there was work on homomorphic cryptography for one operation. Yeah, two strands. There's the homomorphic strand and there's the lattice strand.
Yeah, but they weren't really intertwined.
Yeah, yeah. I mean, well, they weren't. Yeah, they weren't kind of intertwined. I guess it was probably pretty clear early on that you could do like an additively homomorphic lattice-based encryption scheme, because you just kind of like add the ciphertext together and it works pretty well. So it was kind of like a folklore result. I don't know that anyone even bothered to sort of specifically mention it. Maybe probably someone did. But yeah, the difficulty is kind of getting multiplication to work. And so having worked on ntrue, which already used all these polynomial rings, which gave a lattice structure, but also a multiplicative structure in the sense that you can multiply these polynomials together, and things would sort of, you could get it to sort of work where that induced multiplication on the messages. You know, maybe I was, I mean, there's this other researcher who kind of jokingly said, I was just kind of in the right place at the right time, in the sense that I had worked on ntrue and had that in the back of my mind, and that probably helped me a lot to sort of make that jump to getting something lattice-based that works also for multiplication. And then there was the final step, which is a pretty big step too, is that it was still what I had at that point was still somewhat homomorphic, because you could do some additions and some multiplications, but then you get kind of stuck because the error gets too big. So yeah, you need this final step, what we call.
Before we get to that final step, we need to understand the problem Dr. Gentry was having. Let's take a look at a very simple, somewhat homomorphic encryption scheme. First, we pick a random large integer to be our secret key. Let's call it P. Now, we need something to encrypt. Here, we'll stick with a bit, so we have that M is our bit to encrypt, either 0 or 1. Now, to make this scheme more secure, we'll add some padding to our message M, so it becomes M prime. M prime is an integer of the same parity as M, so if M is 0, M prime is even, and if M is 1, M prime is odd. For this example, we'll restrain M prime to be less than or equal to 5. To encrypt our message, we'll pick a random integer Q and multiply it with P to hide our secret bit. By adding M prime, we get our ciphertext C. Now to decrypt, we just take C modulo P. Modulo means we take the remainder when dividing by P. This is the equivalent of setting P equals 0 in the expression. So C mod P is just M prime, and then taking M prime mod 2 or just checking its parity leaves us with the message. Let's try a numerical example. Say we want to encrypt the bit 1. We can pick M prime to be 5, P 10, and Q 43. Now our ciphertext C just becomes 435. To decrypt, just divide 435 by 10 and take the remainder, which is 5. Then, recovering M is trivial. Now, let's show that this scheme supports addition and multiplication. Starting with addition, let's see what happens when we add C1 and C2. Expanding both, we see that both have their own M prime and Q variables, but P remains the same, assuming both were encrypted with the same secret key. Because of this, we can simply factor out P, which leaves us with the intended addition, M1 prime plus M2 prime, and a term multiplied by P. Now, when applying mod P to this expression, we recovered the intended addition. We can use the same process to show that homomorphic multiplication also works in this scheme. Now, these two operations work, but only to a certain extent. Take a look at this. Here are 435 squares. This is the ciphertext from the numerical example earlier. The 5 red squares at the end are M prime. Now, let's put all the blue squares into 43 groups of 10. This is P times Q. When decrypting, we take C mod P, which erases all the groups of 10 and leaves us with M prime. You might have already guessed the problem. As we add and multiply more ciphertexts together, the noise in the message grows too much, eventually becoming part of the multiple of P and getting absorbed by the modulo operation. This is the problem Dr. Gentry was struggling with, only he was building his scheme using ideal lattices, a high-dimensional grid of points. But then, one day, he found the solution.
I mean, that was, if there was any particular aha moment, then that was it. I was actually just in a La Pan Quotidian cafe, I guess not far from here. It's like in 13th Street. And I was just kind of frustrated, honestly, that I had this scheme that worked for just a few multiplications, and so I was just kind of trying to think, is there anything interesting that I can actually do with this scheme? Like, what is the most interesting function that I could do? And yeah, then I thought, well, what about the decryption function? Because decryption in lattice-based cryptosystems is really easy. Basically, it's a dot product and then some rounding.
Okay.
So there's nothing intuitive about this. And in fact, I wasn't completely certain it would all work until it was actually implemented, because it's really hard to keep it all in your brain.
Yeah.
But yeah, you just have to write it out, and if you write it out, I guess the one way you can describe it is that you have this ciphertext that's noisy. Okay. If you keep trying to do homomorphic operations on the ciphertext, then of course it will increase the noise even more, right? Yeah. But with bootstrapping, that's not what you're actually doing. You're not trying to do more homomorphic operations on this ciphertext. Instead, you're taking this ciphertext and you're kind of, in some sense, interpreting it as a circuit.
Okay.
Okay. You're saying, look, I want to take this ciphertext. I don't want to do any more homomorphic operations on it. I just want to decrypt it homomorphically. Okay. And then I can ask, well, is this encryption of the message better than the one that I started with?
Yeah.
because I started with, I already had an encryption of the message in the ciphertext.
Dr. Gentry realized that by bootstrapping the ciphertext, which means computing the decryption function homomorphically, he could obtain a fresh ciphertext with reduced noise. This is the discovery that allowed him to build the first FHE scheme in 2009. Now you may be thinking, if FHE is the holy grail of cryptography, why isn't it being used everywhere? And you'd be right to think that. The implications of fully homomorphic encryption are astronomical. Not only would things like private LLM queries be possible, but in an ideal world where every single bit stored in the cloud is encrypted, then the idea of data breaches or leaks would simply cease to exist. They wouldn't even be possible. You wouldn't have to trust anyone but yourself. Not to mention that all FHE schemes are actually quantum safe, most likely. Now the problem is, there are astronomical, and I mean astronomical, performance hurdles. Just look at how much faster it is to apply a normal image filter compared to the fully homomorphic one I showed before. Even though performance has seen incredible improvement, much faster in fact than Moore's law, the overhead from bootstrapping is simply too much for most applications at the moment. Not to mention, fully homomorphic encryption is just a new kid on the block. Hardware enclaves and multi-party computation have been around for longer and serve a very similar purpose. Still, I think fully homomorphic encryption is a very promising new technology. It has the power to completely change the way we view privacy. Before ending the video, a few quick shoutouts. First off, shout out to Dr. Gentry for coming on and telling the story of FHE. I really do appreciate it. Thank you so much for your time. He also authored a survey titled Computing Arbitrary Functions of Encrypted Data, which contains the scheme I presented in this video. Shout out to FHE.org, the community for all things FHE. I subscribe to their newsletter so I can follow along with any new updates. Shout out also to Zama.ai, which, apart from having the same name as one of the most important battles in history, is a startup developing state-of-the-art FHE libraries. They have a series of blog posts on bootstrapping for the Torus FHE scheme. Their blog inspired the noise animation I made with the 435 squares. Unfortunately, we couldn't get too deep into bootstrapping in this video. Let me know in the comments if that's something you'd be interested in seeing in another video. And of course, shout out to my boy, Gaius Julius.